Remote measurements of cardiac pulse can provide comfortable physiological assessment without electrodes, and the statement as such is the inception behind remote photo-plethysmography. Photo-plethysmography senses cardiovascular pulse wave through variations in transmitted or reflected light. Typically, the ambient light's green channel intensity difference is known to depict the change in blood volume flow based on cardiac pulse. Green channel intensity difference is then signal processed to detect the heart rate. The problems found with current state-of-the-art methods are failure to detect the face or detecting something else's face, motion blur, speed, and range of motion capture. In order to develop a clinically useful technology, there is a need for ancillary functionality such as motion artifact reduction through efficient and robust image analysis. To address the said problems, we've formulated an algorithm which has 3 primary steps. Now let's take a close look at each of the steps. Step 1. Frame capture and color space transformation. A change in color space from red, blue, and green to hue, saturation, and value from literature and experimentation shows the extracted signal to contain less noise with dominant heart rate information. Then, to avoid misinterpretation of face and failure of face detection, we employ an automatic skin segmentation step in our algorithm. It first detects the face, then creates a model histogram of the detected face, which would then be used by back projection to consistently locate the skin region. Following which, the detected face will be tracked using continuously adaptive mean shift function, thus supporting face orientation and enabling lossless face detection for every frame. On completion of skin segmentation, facial key points get positioned based off Kazemi and Sullivan's ensemble of regression trees method, which estimate the landmarks of the face using a sparse subset of pixel intensities, helping achieve high quality predictions. The regions of interest are located in skin regions and, like the key points, are referenced to the face detector bounding box. Step 2. Blur detection, denoising, and motion capture. To estimate heart rate with high accuracy, motion blur-free frames are required, for which, by using the initial few frames as reference, we calculate the blurriness of every other frame using second-order Laplacian responses. Setting the responses from the reference frame as threshold, motion blur-free frames continue to get processed, while the other frames undergo denoising to reduce motion blur. Given Kalman filter's success in motion tracking, it fails to accurately track feature points in this problem because of the highly erratic motion path of the feature points. As observed, the original Kalman filter technique fails to track feature points with precision, especially during direction and displacement change. However, the bounded Kalman filter technique utilizes cubic spline extrapolation to model the trajectory of the previous points and accurately predicts the next location with high accuracy in all direction and speeds, making the proposed algorithm motion robust. Step 3. Signal processing extracted heart rate signals. The extracted raw average pixel intensities per second are concatenated to a normalized 30-second sliding window every second. The signal is then temporally filtered, and using peak detection, the heart rate is found. To test the method, an experiment involving 5 subjects was conducted. Our experimental variables were illumination and motion type. Each subject had to perform 4 types of action in 2 lighting conditions. Result: our method has not failed to detect the face nor its orientation and continues to track the motion of feature points, while other state-of-the-art methods fail to do the same.